Welcome to learning about recurrent neural networks, or RNNs for short. Today, we'll explore how machines understand sequences like sentences, voice commands, or stock trends by remembering past information. You don't need any prior deep learning knowledge. We'll start from the ground up with simple ideas and real-life comparisons. Whether you're curious about AI preparing for a project, or just want to understand how smart apps work, this session will give you a clear mental model of one of AI's key building blocks. Let's dive in and unlock how machines learn from order and time. Let's take a quick look at where we're headed today. We'll start with an introduction to show why handling sequences is so important in artificial intelligence. Then, we'll build your foundational knowledge by answering, what exactly is an RNN, and how does it remember past inputs? After that, we'll go a little deeper into the step-by-step process inside an RNN and how it updates its internal state over time. Next, we'll shift to practical applications, showing real-world examples like text prediction and sentiment analysis. Finally, we'll wrap up with a summary of key takeaways and point you toward next steps if you'd like to keep learning. This roadmap ensures you get both clarity and confidence by the end. Ready to begin the first section? Let's talk about why sequences are so important in AI. Think about language. When you read a sentence, the order of words completely changes the meaning. For example, I am not happy carries a very different message than I am happy, all because of that one word, not. Regular neural networks struggle with this because they look at each word or input in isolation. They don't remember what came before. But real-life data like speech, text, or even temperature readings over time aren't isolated events. They form a sequence where history matters. That's where RNNs come in. They're built to handle these ordered streams by carrying forward information from earlier steps. It's like reading a book chapter by chapter instead of flipping to random pages. This ability to remember gives RNNs a huge advantage when dealing with anything that unfolds over time. So while standard networks might misinterpret not good as positive because good sounds nice, an RNN remembers the negation and gets it right. Pretty smart, right? Now that we see the problem, let's look at how RNNs actually work. Now let's understand what an RNN really is. RNN stands for Recurrent Neural Network. The keyword here is recurrent, which means repeating. Unlike traditional networks that process each input separately, an RNN processes data in sequence one item at a time while keeping track of what it has seen before. It does this using something called a hidden state, which acts like its memory. Think of it like watching a TV series episode by episode. If you miss the last episode, some parts might not make sense. An RNN avoids that by storing relevant info from each step and passing it forward. And here's a crucial point. It uses the same asterisk network over and over again across time steps. It's not copying itself, it's looping back, reusing its structure and weights. This makes it efficient and consistent. So whether it's analyzing the third word in a sentence or the 100th frame in a video, it's still the same network doing the job, just at a different moment in time. Because of this design, RNNs are perfect for any task where history matters, like predicting the next word, translating languages, or detecting anomalies in sensor data. In short, an RNN brings memory to machines. Let's now see how this actually works under the hood. Let's look at how an RNN actually works step by step. Imagine you're feeding it a sentence, word by word. At the very beginning, it starts with a blank memory, usually all zeros. When the first word arrives, say I, the RNN looks at that word and its current memory, which is empty, and updates its internal state. Then it moves to the next word, am. Now it doesn't just see am, it sees am plus whatever it remembered from the I. It blends the new input with its memory, recalculates its state, and prepares for the next step. This continues for every word in the sentence. At each stage, it can also produce an output if needed, like predicting the next word or classifying sentiment. The magic lies in this continuous loop. Input plus memory leads to updated memory, which feeds into the next round. And remember, it's not creating a new network each time. It's the same exact network being reused with the same rules and connections. This is called weight sharing, and it makes the system efficient and easier to train. We often visualize this as unfolding the network through time, like stretching out a spring. While powerful, this setup has limits. We'll talk about those soon. But for now, just picture a smart assistant reading your message one word at a time, getting smarter with each step, always remembering what you said before. That's the essence of an RNN in action. Now that we understand how RNNs work, let's see where they're actually used. One of the biggest areas is natural language processing. Every time your phone suggests the next word as you text, there's likely an RNN behind it. It learns common phrases and sentence structures so it can guess what you're about to say. Translation tools also rely on RNNs to preserve meaning across languages by considering entire sentence context, not just individual words. Then there's speech recognition. When you ask Alexa or Google Assistant a question, it doesn't just match sounds to words, it uses an RNN to make sense of the whole utterance, ensuring call mom isn't mistaken for calm down. Beyond language, RNNs power time series forecasting. Companies use them to predict electricity usage, stock movements, or website traffic based on historical trends. Even in healthcare, RNNs monitor patient vitals over time to flag sudden changes that could signal danger. And in video analysis, they help track motion and activities across frames, like recognizing a person waving or falling. So whether it's text, sound, numbers over time, or visual sequences, if order matters, there's a good chance an RNN is involved. These aren't futuristic ideas. They're already in the apps and devices you use every day. Let's walk through the internal flow of an RNN step by step. Picture a timeline where data arrives one piece at a time. We start at time 0 with a clean slate. The hidden state is initialized to 0, meaning no memory yet. When the first input arrives, say the word I, the RNN combines it with the current state, 0, and computes a new hidden state. This updated state now holds a trace of I. Then comes the second word, love. The RNN takes love and the previous state, which remembers I, and generates a new, richer state that captures I love. By the time we reach you, the network has built up enough context to understand the full phrase, I love you, not just as 3 separate words, but as a meaningful expression. At any point, it can also produce an output like tagging the sentiment as positive or predicting the next word. This entire process creates a chain of connected states, often visualized as unfolding the network across time. But here's the catch. In basic RNNs, the influence of early inputs tends to fade as the sequence grows longer. This is due to a problem called vanishing gradients, where older memories get overwritten or weakened during training. So while RNNs have memory, it's more like short-term recall. That's why later models like LSTMs were invented to hold on to important details for much longer. Still, the core idea remains: use past context to inform present decisions. Let's look at a fun and practical application: text generation. Imagine training an RNN on all of Shakespeare's plays. Over time, it learns the patterns of his language, how he starts soliloquies, ends lines, and uses certain phrases. Once trained, you can prompt it with a few words like to be, and it might continue with not to be. That is the question. How? At each step, it calculates the probability of every possible next word based on what it has seen so far. Then it picks one, either the most likely or a random choice weighted by likelihood. This process repeats, building sentence after sentence. The hidden state ensures that each new word considers the entire history of the generated text. So if the RNN wrote "the king entered the castle," it will later refer to he or the monarch, rather than suddenly switching subjects. Of course, without enhancements, basic RNNs can lose track in long stories or repeat themselves. But even simple versions can produce surprisingly human-like text. Today, this principle powers everything from poetry bots to code autocompleters. The key takeaway? RNNs don't just classify or translate, they can create one step at a time, guided by memory. Another powerful use of RNNs is sentiment analysis, figuring out whether a piece of text expresses positive, negative, or neutral emotion. Let's take a review. Not good at all. If a machine just looked at keywords, it might see good and classify this as positive. But humans know better. The word "not" flips the meaning. An RNN catches this because it reads the sentence in order. First, it sees "not," a red flag for negation. Then "good" arrives, but instead of treating it alone, the RNN combines it with the existing context. Its hidden state remembers the negation, so it interprets "good" as part of a negative phrase. By the end, the overall sentiment is clearly negative. This ability to track shifting meaning makes RNNs far more accurate than keyword-based systems. Companies use this to monitor customer feedback across thousands of reviews, tweets, or support tickets. They can quickly spot dissatisfaction, praise, or urgency, even in complex sentences like "the battery life is amazing, but the screen cracks easily." Here, the RNN detects both positive and negative elements by maintaining separate threads of context. So again, it's not just about words, it's about how they unfold over time. This is why sequence models are essential in modern AI systems that aim to truly understand human language. Now it's your turn to practice. Let's do a hands-on exercise to reinforce what you've learned. Take out a piece of paper or open a digital notebook. Your task is to draw how an RNN would process the simple sentence, "I am happy." Start by drawing 3 time steps, one for each word. At each step, show the input, the current word, the incoming hidden state from the previous step, the updated hidden state going out, and any output like a sentiment label or next word prediction. Use arrows to show the flow of information. As you draw, ask yourself, what does the RNN know at each stage? After seeing "I," it might just know the subject. After "ham," it starts forming a statement. Only at "happy" can it infer positive sentiment. Now imagine if the sentence was, "I am not happy." How would the presence of "not" change the final output? Could a basic RNN handle this? Also, think about limitations. What if the sentence was much longer? Would the RNN still remember the beginning? This kind of sketching isn't just busy work, it builds muscle memory for how sequence models work. Once you're done, compare your diagram to the concepts we've discussed. Does it reflect the looping nature of the network? Is memory flowing correctly? Great, now you're thinking like an AI engineer. Before we wrap up, let's clear up some common misconceptions about RNNs. First, many people think that since RNNs process multiple time steps, they must use different networks for each one, but that's not true. It's actually the same asterisk network being reused over and over again. Think of it like a single chef tasting soup multiple times. Same person, same palate, just at different moments. Second, some assume RNNs have perfect memory. In reality, basic RNNs struggle to retain information over long sequences. This is called the vanishing gradient problem, where early inputs lose their influence as the chain grows. That's why models like LSTM were invented to fix this memory leak. Third, there's a myth that RNNs are only for text. Not true. They work with any data where order matters: audio signals, video frames, heart rate readings, even DNA sequences. The key question is, does the sequence affect meaning? If yes, an RNN might help. By correcting these misunderstandings now, you'll avoid confusion later when you encounter more advanced models. Remember, RNNs introduce the idea of memory in neural networks, but they're just the beginning of the story. Let's review the key points you've learned today. First, RNNs are designed for sequential data, anything that happens in order, like sentences, voice clips, or stock prices. Their superpower is memory. They maintain a hidden state that carries information from one step to the next. Second, they don't use separate networks for each time step. Instead, it's the same network applied repeatedly, sharing weights and ensuring consistency. This makes them efficient and effective for modeling time-based patterns. Third, RNNs are widely used in real-world AI, from autocomplete and translation to sentiment analysis and weather forecasting. They excel wherever past inputs shape current understanding. Fourth, while powerful, basic RNNs have a weakness. They tend to forget older information due to vanishing gradients. That's why improved versions like LSTM and GRU were developed to hold on to important details longer. And finally, RNNs open the door to modern sequence models, including the attention mechanisms behind today's large language models. So even though newer architectures exist, understanding RNNs gives you insight into how machines learn from time and order. If you can explain how an RNN processes "I am happy" step by step, identify where it's used, and sketch its flow, you've got it. Now it's time to check your understanding. Ask yourself, can I explain what an RNN is without looking at notes? Try saying it out loud in simple terms. Next, can I name at least 3 real-world applications? Think about voice assistants, translators, or recommendation systems. Then, do I clearly see the difference between a regular neural network and an RNN? The key is memory standard networks don't carry context from one input to the next, but RNNs do. And finally, could I sketch how an RNN handles a short sentence like, "She runs fast"? Draw the 3 time steps, show the hidden state passing from one to the next, and label the inputs and outputs. If you can do all of this, congratulations, you've mastered the fundamentals. If any part feels shaky, that's okay. Go back to the relevant slide, read the explanation, maybe redraw the diagram. Learning AI is a process, and each review strengthens your foundation. You're doing great. Keep going. You've made it to the end of this fast-track module, and what a journey it's been. You now understand the essentials of recurrent neural networks, how they handle sequences, maintain memory, and power real-world AI systems. But this isn't the end, it's just the beginning. From here, you can go deeper. Want to solve the memory problem we talked about? Learn about long short-term memory networks, or LSTMs. They're an upgraded version of RNNs that can remember for much longer. Interested in how models like ChatGPT work? Explore attention mechanisms and transformers, which evolved from RNN ideas but are even more powerful. If language interests you, dive into natural language processing, where RNNs and their descendants play a central role. And if you love hands-on learning, try coding your first RNN using beginner-friendly tools like Google Colab with TensorFlow or PyTorch. There are tons of tutorials online to guide you. Plus, joining communities like RNMechanelia on Reddit can connect you with others on the same path. Remember, every expert was once a beginner. You've taken a huge step today. Keep curious, keep practicing, and soon you'll be building your own AI systems. Thank you for learning with me. See you on the next module. Thank you so much for completing the I keywords fast track on RNNs. You've now gained a solid, intuitive understanding of one of the most important concepts in deep learning. You know how RNNs process sequences, why memory matters, where they're used, and even where they fall short. More importantly, you've built mental models that will serve you well as you explore more advanced topics. Whether you're learning AI for career growth, personal curiosity, or creative projects, this knowledge is a valuable stepping stone. Remember, you don't need to master everything at once. Revisit this material in a few days, draw the diagrams again, explain it to someone else. It all reinforces your learning. And whenever you use a voice assistant or see a smart reply, you'll know there's an RNN working behind the scenes. Keep that sense of wonder alive. Stay curious, stay engaged, and keep moving forward. You've got this. Until next time, happy learning.